Now we are going to briefly discuss 4 mineral characterization techniques, the XRD, TEM, SEM, and AES. The first one is the X-ray diffractometry. The XRD is a non-destructive characterization technique and a device that measures the intensity of the X-ray reflections from a crystal with an electronic detector, such as an ionization chamber. The intensity measuring device is connected through a suitable amplification system to a chart recorder. Crystal structure and phase identification are performed by comparison of the stored diffraction pattern to databases containing powder diffraction files of known standards. These are some samples of X-ray diffractogram from scientific papers. Minerals such as quartz, feldspar, goethite, and hematite can be detected, among others. You can also compare XRD plots of samples that underwent varying treatments and observe the mineralogical changes. The second one is the transmission electron microscopy. TEM is a technique that provides real images of the particles at the nanoscale. It is necessary to thin the specimen to its final desired thickness of several hundred nanometers using chemical, electrochemical, ion Miller technique, or with the most recent technique that uses a focused ion beam or FIB instrument. This electron microscope is, in many respects, analogous to an optical microscope. However, the source is an electron gun instead of a light filament, so it can produce much more highly magnified images. These are some samples of TEM images. This is a cotton stem under the light microscope, and a more enlarged image can be obtained through TEM. Here at the right side, you can see the TEM images are at nanoscale of 150 and 20 nanometers. Next is the scanning electron microscopy. SEM is a process where the surface of a specimen emits different amounts of electrons as the beam of electrons is scanned across the surface of the sample, producing a signal that is used to generate an image. The optical microscope is the superior instrument at low magnifications with relatively flat surfaces, and the scanning microscope is superior at higher magnifications and with surfaces having strong relief. These are some samples of SEM images showing the microstructure of A356 and A413 alloys. You can see that these images are at microscale. Next is the scanning transmission electron microscopy. The STEM is a type of TEM wherein the electron beam is focused on a fine spot which is then scanned over the sample, and various signals are collected point by point to form an image. It is used to characterize the nanoscale and atomic scale structure of specimens. It has a very high resolution because the specimen is normally so thin that there is not much chance for the electrons to scatter out from the center of the beam in the specimen. Here you can see one example of STEM image in indium oxide with a scale of 1 nanometer. The last one is the Auger electron spectroscopy. Auger electron spectroscopy is a surface analysis technique for determining the compositions of surface layers to a depth of about 2 nanometers for elements above helium. It also has a spatial resolution greater than 100 nanometers, which is about a tenth of that of the electron probe X-ray microanalyzer. It is suited to the studies of grain boundaries in metals and alloys, especially with specimens susceptible to brittle grain boundary fractures. It is useful for surface segregation studies, as in the solving of stress corrosion problems. These are some examples of AES spectrum wherein you can determine the elemental information of thin samples and elemental profiles as a function of depth. So those were some of the mineral characterization techniques. And to wrap this up, let me show you this graph that shows those techniques we discussed along with some of the other available characterization techniques, graphed with their imaging scale and detection ranges. So here encircled are the XRD, SEM, Auger, and SDEM. So thank you, and please check out my references, and thank you also for the design and icons from Canva.